Good morning.
Good morning.
Today, Monday, and let's start sharing the screen. Okay, today let's start recording, right? Stop recording. Okay, we're already recording, right? Yeah, we're already recording. And today is March the 30th, Monday. And where did we stop? Let's take a look where we stopped it here. We are talking about the magnetic field, and we are covering chapter 21 of the book. Right here. Okay. Let me get. So we need to start talking about Ampere's law, but let's get the book here. Chapter 21. That's right in here. Okay, so here you go. We have magnetic fields. That's something that has been known for a long time, since antiquity. And force that a magnetic field exerts the moving charge. Crawford covered that, right? The motion of charged particle in a magnetic field. If we are talking about a magnetic field, a particle that has a velocity vector perpendicular to the magnetic field undergo a circular motion, uniform circular motion, right in here. This is the case of a uniform magnetic field, a particle with a velocity vector perpendicular, a charged particle with a velocity vector perpendicular to the magnetic field undergoes a circular arc in the field. Okay, and we have this device that's called the mass spectrometer, and the device out there that's sold out there, okay, that we use to find out the type of charged particles. I think I'm gonna do that. Did Crawford cover the mass spectrometer, by the way? Can you recall? Do you recall if Crawford covered the mass spectrometer during his?
I don't remember hearing
Okay,
that.
I think I'm gonna do that. This is an important device. Is applications, right? This is applications of the magnetic field. And the force on a current on a magnetic field, right? I did that, and the torque on a current carrying wire, current carrying coil. I covered that with lots of details. I told you that the magnetic field. How can we produce a magnetic field? What's the source of a magnetic field? The source of a magnetic field is an electric current. That's what the sort of the magnetic field is. Okay, and so let's cover the mass spectrometer. I think is a fun topic to cover. And then we finish the chapter with Ampere's law. I'm not going to do magnetic materials. And let's talk about the mass spectrometer. Let's see here. Okay. But before to cover the mass spectrometer, we also have to cover the velocity selector, okay? I don't think the book has the velocity selector there, but it's important. It's an important thing to do. Let's see if we have velocity selector here in the book. Yeah, let's cover the velocity selector before we cover the mass spectrometer. The book doesn't have, but it's important for you to know about it. So don't forget that what they're teaching here is something that has practical applications. Okay? People, for instance, they fly the velocity selector in space to map the distribution of charged particles in the interplanetary medium. And now is the Voyager spacecraft to map also the distribution of charged particles in the interstellar medium. The Voyager 1 and 2 became the first spacecraft launched by humans, right, to reach the interstellar medium of interplanetary spacecraft that has flown in the interplanetary medium. There's a bunch of them out there, right? And let's talk about let us talk about two important devices that use the electric and magnetic fields to characterize charged particles. Okay, to characterize these devices. These devices are one, the velocity selector. Two, the mass spectrometer. Okay. The velocity selector is exactly what the name says. The velocity selector is exactly what the name says. It selects charged particles that have a given velocity or energy, right? Or energy. a charged particle that has a mass and a given velocity has kinetic energy. So I can also say that is when we are selecting a particle with a given velocity, we are also selecting particles with a given energy. And it's exactly what the name said. It selects. It uses the electric and magnetic fields to select charged particles that have given velocity or energy. Okay. The mass, on the other hand, the mass spectrometer is used to measure not the mass of a charged particle, okay, but the mass to charge ratio of a particle, of a charged particle. So that's what the mass spectrometer does. It measures the m over q, or the q over m, or the q over m, okay? That are those two devices do. What those two devices do. And let's take a look at our illustrations. Magnetic field right in here. Okay, here you go, the magnetic fields. The magnetic field of the Earth, right, is slightly shifted from the geographic poles of the Earth, displaced, slightly displaced. And here you go, here's the charged particle in a magnetic field. A charged particle that's at rest in a magnetic field does not experience any magnetic force whatsoever. If the velocity vector is parallel to the magnetic field, it still does not experience any magnetic force whatsoever. But then if you have an angle, if the velocity vector of the particle makes an angle with the magnetic field, now the particle is going to feel a magnetic force. A magnetic force that's given by the right-hand rule. The right-hand rule, okay? And it doesn't matter the angle. It can be an angle that's different of 90 degrees. In this case, the particle is still going to feel a magnetic force, but the motion of the particle is going to be slightly different from the motion from this case here. Okay, in this case, the particle undergo a uniform circular motion. In this case here is going to be something slightly different, okay? And we use this type of knowledge. Let's see, direction of the force. Oh gosh, this thing's supposed to be a negative charge, okay? If you have a negative charge, the force is into the board because of the Q here. Here you go, this one a positive charge, right? This one is a positive charge, so the direction of the force is correct. Okay, Q less than 0, the force is going to be on the other direction. Okay, notice that it depends on the charge. If the charge is positive, the cross product between the velocity and the magnetic field, the right hand, right? The right hand rule that we use, V. You point your hand along the V vector, and then you curl your hand towards the direction of the magnetic field. The thumb indicates the direction of the charge, of the magnetic force. That's for the positive charge. For a negative charge, you repeat the procedure, right? palm of the hand along the velocity vector. You curl the palm of your hand towards the magnetic field. The thumb points in this direction out of the board, but because of the negative charge, the direction of the field is inverted. That's why I put the direction of the force into the board. Okay? There are more than one way to do the right hand rule. Let's take a look here in the book. The book has a different way of doing the right hand rule. Make sure you understand that, right? Here you go. That's another way of doing the right hand rule. Let's see. Not this one. I don't want this one. I want the other one. And the different ways of doing the right hand rule results exactly in the same direction. Here you go. Here's the right hand rule done in a different way in the book. Okay. You point the palm of the hand in the direction of the magnetic field and the thumb, that's the right hand, in the direction of the velocity vector. If we have a positive charge, the magnetic force points away from the palm of the hand. Okay, if the electric charge is negative, then the magnetic force points into the palm of the right hand. That's another way of doing. I prefer this one here that I did for you. Okay, I prefer this one. Point the palm of the hand towards the velocity vector. Okay, towards the velocity vector, and sometimes you have to do. Here you go. Let's see here. Sometimes you have to do something difficult here. So palm of the hand towards here you go. Yeah, this way. Curl towards the B field, and the resulting magnetic force is downwards. Okay? So practice those two different ways of determining the magnetic force of a charged particle. I'm going to write that down here for you. In order to understand, these two devices, you must understand the magnetic force applied to a moving electric charge. Okay? Okay. So 4 important situations that you must understand about the magnetic force. 1, a charged particle that is at rest in a magnetic field experiences no magnetic force whatsoever. 2, a charged particle that has a velocity vector along the magnetic field direction experiences no magnetic force as well. Okay. Now, a charged, another situation here. That's an experimental result. A charged particle that has a velocity vector that has velocity vector that makes 90-degree angle, a 90-degree angle with the magnetic field experiences a magnetic force that is equal to QVB. Okay. With a direction that is given in terms of the right hand rule. Okay, there are at least two different ways of using the right hand rule, RHS. Right hand rule, RHR, okay? Not RHS, RHR, right hand rule. Okay, let's see. One. Point the palm, extend, here you go, one. Extend the palm of your right hand along the direction of the velocity vector of the particle. The right thumb must make the right thumb with the right thumb making a 90 degrees angle with the palm of the hand. Okay. Curl the palm of the hand towards the direction of the B field. Okay, and let's see here. I'm going to do it this way. I'm saying that there are two different ways, right? So the way that I prefer, right? The way that, not the way that I prefer, but the way that most books teach, okay? Your book teach in a way that it's not common, but it's still a good way of visualizing it, okay? Curl the palm of the hand toward the direction of the B field. Extend the palm of the right hand along the direction of the velocity vector of the particle, with the right thumb making a 90-degree angle with the palm of the hand. Curl the palm of the hand towards the direction of the B field. Okay. The right thumb points along the direction of the magnetic force. That's one way. The way that the book does. Okay. The way that the book does is important because sometimes, do you see the difficulty I had to do that problem with the right hand using my technique? Sometimes it's very difficult to orient properly your hand using this technique that I passed to you, right? But the technique of the book prevents you from doing all that contortion with your hand. Okay, the way the book teach, most books, right? Not your book, but most books, not your book. Let's put here, not your book, but most books. The way your text book teaches Okay, this technique is has the advantage that it prevents you from doing some contortion, right? With your hand. So how is that? How does it go? Let's go back to the illustration in the book. Still the right hand. Doesn't require you to curl the palm of your hand. And so we can, the way your textbook teaches, this technique has the advantage that prevents you from doing some prevent you from contorting, right? Contorting your hand, and you do not have to move it. And you don't have to move it at all. So that's the advantage of this technique. So how do we do? You know, extend the palm of your hand, right? Just like first step. Oh, what's happened here? Extend the palm of your right hand. With the right thumb, I'm going to eliminate this one here. With the right thumb, making a 90-degree angle with the palm of the hand. Both, and I'm going to elaborate here. Both the thumb and the palm of your hand must lie in the same plane. Okay, and I'm gonna put that here as well. Right? So here you go. Here's the palm of my hand. The thumb is making a 90-degree angle with the palm of my hand. And the thumb lies in the same plane of the palm itself. It's not like that. In this case, the thumb is not lying in the plane of the palm of the hand, right? You have to keep your thumb in the same plane of the palm. Okay? What else? In this technique of the book, point your thumb along the direction of the velocity vector of the particle, of the charged particle. Right? Yeah, the particle must be charged. A neutral particle does not experience any magnetic force whatsoever. Okay, like so I'm gonna even put it here. You go. A neutral particle, a neutrally charged particle, right? Experience no magnetic force whatsoever. So point your thumb along the direction of the velocity vector of the charged particle. Going back here, right? Point the palm of your hand along the direction of the magnetic field. Point the palm of your hand along the direction of the B field. Okay? If a particle has a positive charge, comma, the magnetic force makes an angle of 90 degrees. 90 degrees with the palm of your hand. And points away from your hand. Now the opposite is true, right? If a particle has a negative charge, the magnetic force still makes an angle. Magnetic force still makes an angle, makes a 90-degree angle with the palm of your hand, but points towards your hand, towards the palm of your hand. Okay, if a particle has a positive charge, from the palm of your hand. So two different techniques to find out the direction of the magnetic force. One very important characteristic of the magnetic force. The magnetic force will always be simultaneously perpendicular to the velocity vector, and the B field vector. The velocity and B field vectors. To the velocity and the B field vectors simultaneously, remember? The velocity vector doesn't have to be perpendicular to the B field, but the magnetic force will always be simultaneously perpendicular to the velocity vector and the B field vector. That's, let me copy that technique right in here in the book. I'm gonna paste into my notes. Two different ways. Okay, here you go. Okay. And you can look at the internet for other ways. There's another third way of doing the same technique, okay? But let's stick to those two for now. And if you want to learn a little bit more the right-hand rule, right? Just look at the internet. There is one third technique. Right-hand rule for the magnetic field. Here you go. That's another one here. This is another right-hand rule. A third one. This one is the one that your book shows, right? But they don't illustrate the one with the curled hand. The curled hand is the one that I was taught when I was taking this course. Giga. Conventional. So 3 different techniques. I'm not going to illustrate this one. Okay, so, but if you want to get familiar with that, you can look at that. Okay, so having said that, what time is that? 10:15, right? We still have time. Here is the, now, if I go ahead and reorient my magnetic field, okay? Here you go. See, the magnetic field is in this direction. This illustration here is exactly the same illustration. Let's see. Yeah, this illustration that you see here is exactly the same illustration as this one, with less lines there, okay? Velocity vector in the horizontal direction, magnetic field in the vertical direction, right? It's exactly the same illustration that you saw there. Q greater than 0. Negative charge, magnetic force into the board. Velocity vector, making an angle with the B field. The magnetic force is still in the same direction. But now the formula for the magnetic force is this one here, the more generic formula, right? Let's write that down here. If the velocity vector makes an angle theta with the B field, then the magnitude of the magnetic force is given by let's get the equation here. It's given by, here you go. Oops. Magnetic force is given by QVB sine of theta. So that's the most generic equation for the magnetic force. If the angle of where theta, right? Yeah, this is the angle between the velocity vector and the B field. If theta is 0, right, sine of theta is going to be 0, and the magnetic force is going to be 0. If the charge is 0, the magnetic force is also 0. Okay. If the angle between V and B is 90 degrees, you get QVB just like I told you right in here. Okay. So item 1, item 2, and item 4. Oh, and also item 3, right? Item 1, 2, 3, and 4 are just special cases of this equation that you see right in here. Also, here you go. If V is equal to 0, right? As we discussed before, let's see, let's put here, note that items 1, 2, 3, and 4 above are special cases of the above equation. Item 1, Item 1 is for Q equal to 0. Right? So item 1, neutrally charged particle. Q equal to 0. I want to put that as an item 7 here. So we can organize everything. Good. Items 1, 2, 3, and 4. For a special case of the above equation. So here you go. Item 1 is for Q equal to 0. B, item 2 is for V equal to 0. Right? Item 3 is for V different of 0, but theta, right, equal to 0. I'm going to put it here, you know. Theta is the letter Q, okay? In case you want to know. You go. Theta equal to 0. Let's see, theta. Item 4 is for theta equal to 90 degrees. Like that. So now that we have gone through this extensively, right? Now I'm going to reorient the magnetic field so you can have a better look at the motion of the charged particle, right? Motion of the charged, we're talking about uniform, okay? Of a charged particle in a uniform B field. Uniform B field means that the field does not change. So here you go. And in order to illustrate that in a better way, I'm going to orient my B field in a different way. Instead of putting the B field in the plane of my screen, right? I'm going to put my B field in a direction perpendicular to the plane of my screen. What does it mean? What does this drawing mean? This drawing means that the B field is pointing towards you, towards us. Okay. So that's why I put in the next screen, I put the B field here. I'm putting my X and Z axis in this plane. When we have the X and Z axis in this plane, it means that my Y axis point towards the screen, okay? Let's see if I'm going to illustrate that here for you. Let me illustrate that here for you. PowerPoint. I want, oh, here you go. That's the one I want. Okay, and I'm going to send it to the back. No, don't send to the back. Keep this way. Keep this way. I'm just going to change the transparency. Let's see if I can change the transparency here. No, that's not the one. Size and position. Let's see. The transparency must be here. No. Fill. Yeah. transparency is right in here. I want you, okay, yeah, not good because the axes are going to overlap with my cross. Okay, so let's leave this way, and no solid fill, and I'm going to put white. Yeah, let's put this way. I want to make just a little bit transparent so you can see that there's an axis there behind, right? And what am I doing here? I am illustrating the direction of the y-axis in the three-dimensional space, right? X cross y points in the direction of the z-axis. Y cross z point in the x direction, and the z cross x point in the y direction. Right-hand rule, I'm doing that right-hand rule here. So in this case, the B field is along the negative direction of the y-axis. And copy and paste. I'm going to put my charged particle right in here. Notice it has a positive charge. I still didn't put the direction of the velocity vector. I'm going to put the direction of the velocity vector right now. And I'm going to put it in a different color. So here you go. Red, red, right? That's the velocity. The velocity vector is in the minus x direction. Minus x direction. We have one more. V perpendicular to B, right? Use the V perpendicular to B case. Here we go. We don't need that anymore. I'm gonna copy that. Here you go. Paste like that. Let's see what would that be. Let's see here. This one. So what I need to do is to copy V cross B that you see right in here is just the mathematical notation of that operation that we did with the right hand, okay? That plus the sine of theta, plus the sine of theta. No fill. Let me put it down here. Okay. Be perpendicular to B. Okay. And now I'm going to illustrate the magnetic force with a different color. I'm going to illustrate the magnetic force with a different color. Here you go. This one is going to be the bluish, right here. And now we have this particle moving with the velocity vector that's perpendicular to the magnetic force. And that's the only force that's acting in the charged particle. That's the only force that's acting in the charged particle. So what we have right here, magnetic field along the negative y direction, velocity vector along the negative x direction. We end up with a magnetic force that's along the positive z direction. We need to cover that so you can understand those two instruments that we're talking about, right? That's why I'm doing that. Copy and paste. By the way, it's lots of work to do this type of illustrations, okay? Since I have been teaching this course for a long time. I have lots of those illustrations here. This one should be erased. We don't need that anymore. Here we go. What do I have to do now? I have to get this charged particle here. Okay, so when you have a force that's perpendicular to your velocity vector, you do not change the speed, you do not change the magnitude of the velocity vector. You change only the direction of the velocity vector. That's what we learned in physics 6. Remember that? Force, centripetal force, right? Perpendicular to the velocity vector. The direction of the velocity vector changes, but not its magnitude. And that's exactly what's happening to this charged particle. So, and we end up having a uniform circular motion. Here we go. One right in here. Oh, I don't want this one. This one that I want. Oh, yeah, this one that I want to change. The velocity vector is going to be tangent to the path. The velocity vector is always tangent to the path. The magnetic force perpendicular to the velocity vector. I want to make sure that I made them perpendicular to each other. That's why I'm putting this square right in here. Yeah, right that. Okay. Send to the back. No, I don't want to send to the back. Maybe this one I want to send to the back. This one, yeah. Now the square is still there. To indicate that what we have is a 90-degree angle. Initial position. And by the way, I need another circle right in here. So I can play my movie, right? First frame of my movie, second frame of my movie. And in the second frame of my movie, I want to move this V here as well. I don't want that anymore. But I want this one. My charged particle is going to move somewhere around here. The velocity vector, I am repositioning the velocity vector as well. And the magnetic force vector right here. And now we have our movie, right? 3 frames, a 3-frame movie. Here you go. That's how the particle moves when the velocity vector is perpendicular to the magnetic field vector. We don't need that anymore. And we are going to use this knowledge for those 2 devices that I mentioned to you. Okay. And by the way, I talked about the Crookes tube, remember? The Crookes tube is a real life illustration of what happens with those charged particles when they are subjected to the magnetic field. I showed you a YouTube video. And that's something that we have at the college. Yeah, I like to show that to my students when I'm teaching that in person. Okay. Now let's talk about the velocity selector, right? Now that we know how the particle moves with the applied magnetic field, uniform magnetic field, now we can start talking about the velocity selector. The velocity selector is a device that employs a uniform electric field, okay? Two plates, two parallel uniformly charged plates, and a magnetic field. The magnetic field is perpendicular to the electric field. That's what you need to come up with a velocity selector. Let's see. From field, a particle, a charged, I gotta document that here, right? A charged particle with a velocity vector perpendicular to a uniform B field will undergo, let's put it this way, will undergo uniform circular motion in a plane perpendicular to the B field. Okay, and I illustrate that right in here. This circle, right, has a plane that's perpendicular to the magnetic field. We don't need that. What's doing that here? We don't need that either. What else? Yeah, that's good. Okay. Now let's talk about the velocity selector. The velocity selector device. The velocity selector, The velocity selector is a device that selects that, the velocity of a given charged particle. Basically what it does, in other words, a charged particle with a velocity tuned to the settings, right? To the settings of the velocity selector, will move with constant velocity within the volume of the velocity selector. That's what the velocity selector does. And I'm gonna elaborate that with you, how exactly it works, okay? The velocity selector is made up of one uniform electric field and another uniform B field perpendicular to each other. Okay? And the illustration of the velocity selector is right in here, right? Electric field in the horizontal direction, magnetic field coming out of the plane of the screen. Okay? Both fields are uniform. The only difference is that one is an electric field, the other one is a magnetic field. And then let's see how the velocity, what I have right in here is a velocity selector device. Somehow we generate this magnetic field. There is a way to generate a magnetic field. I didn't explain to you how to do that, but there is a way to do that. Okay, there's a device, a very important device out there that we can use to generate a magnetic field. But I will tell you about that further down the line, okay? But just believe that it's possible to generate a uniform magnetic field and a uniform electric field. And now, what else do we do? Suppose that we have this charged particle within this volume. This charged particle, in this case, will be attracted towards the negative plate of your parallel plate capacitor, right? It's a positive charge, so it will be attracted towards the negative side of the plate. The particle will move in the direction of the electric fields. If the particle is at rest, then the particle just moves to the left but it will move to the left with an acceleration, right? So the velocity selector in this case, for a particle at rest wouldn't work. So in order for the velocity selector to work, the particle must have a given velocity just before entering this volume that you see right in here. Okay? Now that you have this velocity vector, you will end up having a magnetic force, right? Do the right-hand rule again, V cross B, that's going to point to the right. Do you see here? Depending on the velocity of your particle, right? If the velocity, I'm gonna do an illustration here. Here you go. If the velocity is smaller, the magnetic field is going to be smaller as well. Can you picture that? But the electric field is not going to be affected. But the electric force is not going to be affected. It's not going to be affected because the electric force depends only on the charge and the electric field. Okay? So depending on the velocity of the particle, you're going to have a stronger or a weaker magnetic force. Let's do that. Let's do another illustration here. So suppose now that the velocity is a larger velocity, right? The magnetic force is going to be stronger, right? It's going to be like that. It's going to be even stronger than the electric field, than the electric force. Do you picture that? Can you picture that? Okay. So 3 different situations, right? Here you go. What I want to do, let's see, I want to put this one right in here. Velocity of the charged particle has a given velocity. And then my magnetic field for this specific velocity is going to be larger than the electric field, right? Velocity a little bit smaller, then the magnetic field is going to be equal to the electric. The magnetic force is going to be equal to the electric force. Can you picture that too? Right? Electric force is Q times E. And if this velocity of the particle is going to be smaller, then the magnetic force is going to be weaker. So what's happening here? This velocity selector is selecting specifically this particle with this velocity because the magnetic force and the electric force are the same, cancel out each other, right? And the path of the particle is going to be along this line. Okay? The particle is not going to veer to the left, it's not going to veer to the other direction either, right? In this specific case, right? In this specific case, for instance, that we don't have the particles at rest, the particle is just moving completely to the left, right? And the velocity selector doesn't work for this particle, okay? In this specific situation, okay, in this specific situation, the velocity of the particle is matched to the velocity selector configuration. And the particle does not veer to the left and does not veer to the right either, because those two forces are canceling out. Okay? In this case here, in which the electric force is smaller, right? Is similar to what we saw before, the particle will veer to the left. And in the other situation here, in which the magnetic force is larger, where is that magnetic force larger? Okay, right in here. The particle will veer to the right. So the velocity, this specific velocity selector here is tuned exactly to this particle with this specific velocity. Okay? And how do we detect this particle? Well, we do the following. We put a detector here. It can be a phosphorescent screen, okay? Phosphorescent screens, they will glow whenever a charged particle impacts it, just like you saw in that video, in that YouTube video of the Crookes tube. So that's how the velocity selector works. Okay, and that's, let's see here, 1048. Let's document everything that I said here. I'm going to here an illustration of the velocity selector. Illustration of the velocity selector. E field perpendicular to the BE. Uniform field perpendicular to the B uniform field, to a B uniform field. Here you go. To a B uniform field. Okay, so here you go. Charged particle at rest in this volume. Let's see. I want to hit this one here. Q greater than 0, and I'm gonna put it V equal to 0. Okay. Why is this thing is? Let's see here what's going on here. It has this. Okay, good. Now let's do it. V at rest, right? V at rest. Copy only. Positive charged particle at rest inside the velocity selector. Veers, right? Veers to the left. Here you go. Here's to the left. Then you have this situation. Charged particle with a velocity vector perpendicular, simultaneously perpendicular to the electric and magnetic fields, and having a specific velocity where both the magnetic and electric field cancel each other out, are selected to travel in a straight line with constant velocity. That's what the velocity selector does. Here you go. Positively charged particle with a velocity vector simultaneously perpendicular to the E and the B fields and having a specific velocity, and that is matched to the velocity selector, comma, travels with constant velocity in a straight line. Straight line. Okay, here's the case. In this case, both the electric and magnetic force cancel each other out. In this case, both the electric and magnetic forces cancel each other out. Okay? And we can find out exactly what is the electric and magnetic field for this specific situation. We can find out the exact relation between the velocity of the particle in terms of the E and B fields for this specific case. Okay? For something like that to happen, for the net force, here you go. For the net force to be, we're gonna go in our break very soon, okay? For the net force on the charged particle to be 0, we must have the following relation. I need to get my equations here. Insert equation. Here you go. Electric force equal to magnetic force. Okay, electric force is Q times E. Magnetic force is what? QVB, because the vector velocity of the particle is simultaneously perpendicular to the B field. Perpendicular to the B field. Okay, so notice that the Q cancels out. So this velocity selector does not depend on the charge of the particle. And we have this situation in which, here you go, if the velocity of the particle is equal to the ratio between the electric and magnetic field, the particle will move with constant velocity within this volume. The above equation states the following. if the velocity of the charged particle is equal to E over B, this particle will move with constant velocity within the volume of the velocity selector. Okay. Also, note that this velocity is not affected by the charge of the particle. It's not affected by the charge of the particle. It's independent whether you have, a very large charge or a very small charge. If their velocities are tuned to this ratio that you see here, they will both move with constant velocity within the volume, right? So that's what we need to cover for the velocity selector. I think we still have like 2 or 3 more minutes to do. Let's do another illustration here. Let's take 3 minutes before we go in our break. It's 10:57 right now, and I have this. You go the particle at rest, right? The particle with the exact velocity tuned to the velocity selector, and now the particle with a velocity larger than that of the velocity selector for, let's see here, for this case, for this situation, whenever f of b greater than f of e, the particle will veer initially to the right, right? That's the case here. Here you go. Initially to the right. So those are the 3 situations that we have, If 3 situations, right? 3 situations. Let's see if we have time to do that. 3 situations. 1, if particle is at rest, it will move towards the negative plate of the capacitor, right? If electric, it will move towards the left, okay? The left side of the velocity selector, If particle has a velocity below E over B, it will still move towards the left side. If particle has a velocity equal to E over B, it will move upwards with constant velocity. If particle has a velocity greater than E over B, it will initially move to the right. Okay, so we have we conclude here with the analysis of the velocity selector. Now we can go in our break. Any questions before we go to the break? That's 11:01 a.m., right? 11:01 a.m. So that break from 11 a.m. to 11:16 a.m. If you don't have any questions, I will see you in 15 minutes. See you then. Okay, I'm back here. I forgot to show you the syllabus, right? Just for us to have an idea where we are in the course. So here you go, Monday, March the 30th. We're still reviewing the magnetic field chapter 21, and hopefully we'll be able to start chapter 22. Let's see, here you go. On Wednesday, we're going to have lab 3 and reports. Here you go. Reports for labs 1 and 2 due. Okay, that's what we're going to do on Wednesday. And next week, we are going to have a whole week off because of spring break. Then we meet again before the second exam. For the second exam, which is going to include labs 1 and 2 and chapters 20 and 21, right? Chapters 20 and 21. Exam 1, 9:40 to 11:40. Okay, so that's the situation we have right here. Any questions? So now let's go talk about the mass spectrometer. Okay, let's talk about the mass spectrometer. You learn about the velocity selector. Let's talk about the mass spectrometer. Now, that's how the velocity selector works. Let us talk about the mass spectrometer. It's all about measuring the properties of a charged particle. That's all that was all about. The velocity selector, like I mentioned before, is usually launched in the interplanetary space to make a mapping or to find out how is the distribution of the charged particles in the interplanetary space. That's one application of this device. And what about the mass spectrometer? The mass spectrometer is the device that incorporates the velocity selector and something else. The mass spectrometer is a device that is the velocity selector plus something else. Okay? So here you go. You already know that a charged particle undergoes uniform circular motion in a uniform magnetic field. You already know that. Okay, so, and the mass spectrometer uses this specific characteristic of the motion of the particle motion, to find out the charge to the mass ratio. Okay, so let's see how the mass spectrometer works. Right here we have the velocity selector with the charge inverted, right? The positive plate is this one in the left, the negative plate is this one in the right, and on the top of that, the magnetic field is into the board. And we have this region, right? The inner region of the velocity selector, and we combine the velocity selector with another region outside the velocity selector that has only a magnetic field. Okay? Notice that I put here inside, right? Magnetic field on the inside of the device and magnetic field on the outside of the device. Here we have both an electric and magnetic field, and here we have just a uniform magnetic field. What you see right in here is a slit that lets only certain particles pass through this gap that you see here. Okay? And then what happens? Okay, we have these particles, this specific velocity, tuned to the magnetic and electric field within this volume. Is going to move in a straight line towards this slit. And once it enters this outside region, what's going to happen? What's going to happen? There will be only a magnetic force acting in the particle. Okay, V cross B, right? V cross B. V, let's see, VB. V cross B is to the left. And then at this point here, the particle will undergo uniform circular motion. And it's going to strike this screen right here. And this screen is a special screen. It's a screen coated with a phosphorescent material that's going to give out some luminosity once the particle, the charged particle, collides against it. That's how it works. And you also have a ruler here, a ruler to find out exactly what's going to be the position that the particle is going to strike the screen. That's how the mass spectrometer works, okay? Phosphorescent screen, the mass spectrometer, velocity selector plus a slit, plus an external magnetic field, plus a phosphorescent screen, okay? New device, let's see, here you go. The mass spectrometer is made up of the following devices. One, the velocity selector. Let's write that down like that, right? The velocity selector. Two, a slit. And I don't want to, new device, the mass spectrometer. I slit. Three, an external magnetic field outside, an external magnetic field outside the velocity selector volume. Four, a phosphorescent screen to visualize the impact of the to visualize the position where the charge impacted the phosphorescent screen. So those are the pieces of the puzzle of the mass spectrometer. Okay? It all depends. It depends on the velocity of the position, right, of impact is going to depend on the velocity of the particle, but it's also going to depend on the charge of the particle. The faster the particle is, the larger the radius of curvature of the particle. And we can calculate that too, okay? So let's talk about, here you go. Now let's talk about the mass spectrometer, right? The mass spectrometer is a combination of the following devices. One, the velocity selector. Two, that we explained before, a slit, right? A slit through which the electric charge passes through. An external, a magnetic field, here you go, a magnetic field. External, outside, right? Outside the volume of the velocity selector. A phosphorescent screen. A phosphorescent screen to visualize the position, a phosphorescent screen position of impact of the electric charge in, okay, this position provide us with the radius of the circle undergone by the charged particle. Okay, like that. And I'm going to copy this illustration here. Like right here. Copy. And I'm gonna go through the mathematical derivation of what you get. Because let's see if I can get that. No. Yeah, okay. Okay, let's go through that again. A charged particle with a specific velocity that matches the electric and magnetic forces, so it can move with constant velocity. So this charged particle passes through this slit, and in this region, we have a uniform magnetic field, different from the magnetic field, not necessarily equal to the magnetic field on the inside. Okay, and once this particle is subjected to this outside magnetic field, because we have only a magnetic field, this particle will undergo uniform circular motion, okay, and will impact this screen here that has a phosphorescent material. When the particle impacts the screen at this point, for instance, you see a glow coming out of the screen, and from this glow, you can measure the diameter of the circular path of the particle. That's how it's done, okay? That's how it's done. And let's see what we can obtain from this information. From note that from this device, you can measure the diameter of the circle under the particle that the charged particle undergoes. So let's take a look at the radius, the diameter, right, of the circle. What we can find out from the theory that we have covered so far, okay? The situation is like following. We already know that the particle is undergoing uniform circular motion, right? So what we have a centripetal force that's going to be equal to the magnetic force. Okay? And the magnetic force, you already know it is given by QVB, right? QVB. But the centripetal force from physics 6 is also equal to mv squared over r. R is the radius of the circle. And now we can plug this equation right in here. Okay. Notice that the centrifugal force depends on the velocity of the particle. And the velocity of the particle depends on the inner electric field and the inner magnetic field. What can we simplify here? We can simplify V and V. Okay, but V is also given by that equation that you saw before. Is E over B, right? And by the way, this B here, we must emphasize that this B here is the external field, external magnetic. I put out, right? Let's put the outside magnetic field, not external, but outside magnetic field. 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 But we also know from the previous device that the velocity of the particle is given by the inside electric field divided by the inside magnetic field. Yeah. E over B. I am making a distinction, right, between those two magnetic fields, the magnetic field on the inside and the magnetic field on the outside. I can go ahead and substitute this V in this equation right here. And from this equation, we can find out what would be the charge to mass ratio or mass to charge ratio of this charged particle. And let's see, I'm gonna put my Q right in here, right? I eliminate the Q. I pass the R, the radius of curvature of the circle, to the other side, right? I pass the magnetic field on the inside to the right side, and the electric field on the inside to the right side. These are the radius of the circle is measured with the mass spectrometer. And that's what we end up getting for the mass to charge ratio, or the charge to mass ratio, whichever way you want to. Can get the inverse here too, right? Q over M. Let's see, this one, E in, B in, B out, R. That's another way of writing down the same result. Let's take a look here at the mass spectrometer. Okay. Here, the detector here in your notice that he didn't include the velocity selector here in this case. But this ion source, this device that you see right here, is doing exactly the same role as the velocity selector. The charged particle is being accelerated by this electric potential that you see right in here. Here is my slit. Here's the magnetic field that I mentioned to you, right? Depending on the mass of the charged particle or the velocity of the charged particle, you get a smaller circle or a larger circle. The detector that you see here is nothing more, nothing less as our phosphorescent screen that I mentioned before. Okay? So it's the same device illustrated in a different way. Well, you go. What happened here? Oh man. Let's go back here. Yeah, okay, here you go. The equation here that you see right in here is given in terms of the voltage that you got the ion accelerated. Okay, that's what you have here. We have a different equation because the setup is different. But what you see, right, MVEB, right? MVEB, let's take a look. What's MVEB? MVEB is the let's see. And VEB is the ratio. Let's see. I didn't calculate the ratio for you. Did I calculate the ratio for you? Yeah, I didn't calculate the ratio for you. And let me write that down here. Not the ratio, the radius, right? The radius is given the radius of the charged particle, where R is given by, okay, R QB out over MV. MV. and the V depends on the electric potential. And VEB. R is MVEB. Well, let's see. We have a different equation there. What is that? Let's see what's happening here. MV, let's see if I got it right. MV square over R. Yeah, MV square over R. This V cancel out with the V. Okay. MV over, oh yeah, so it looks like I made a mistake, right? Nobody knows see that, right? Let's do it again. Yeah, I made a mistake here. I inverted. Okay, let's do that again. If R goes to the other side, right? Let's see. I'm gonna do step by step so I don't make the mistake again. Okay, here you go. This term goes to the other side. You'll be out. You'll be out. MV over QB out. And now we have the same equation. Okay, MV over EB. Yeah. He put the electric charge of the electron here. It's not necessarily the charge of the electron. Because if it's an ion, okay, if it's an ion, the ion doesn't necessarily have the charge of the electron, can be twice the charge of the electron, 3 times the charge of the electron, okay? So that's how we calculate the radius of the particle. And that's what we have for the mass spectrometer. And now we can get into the Ampere's law. I walked you through the torque, right? And current carrying loop. Current carrying loop. You already know that magnetic field is produced by a current. The source of magnetic field is a current. And now we can start talking about Ampere's law. Okay, let's talk about the laws of physics again. Laws of electricity and magnetism. Gauss's law of electricity. Yeah, the electric flux, a closed volume. See here. enclosed volume. Closed volume. That's the first law that I introduced to you. Q enclosed divided by epsilon naught. Okay, like that. Closed, not enclosed, but closed volume. Closed volume. And then we have Gauss's law, the electric flux, right? And for Gauss's law of magnetism, the magnetic flux in a closed volume is going to be 0. That's the law that states that there is no magnetic monopole. Magnetic monopole. And now we are going to talk about another law, which is the Ampere's law. Ampere's law. Ampere's law is the law that allows you to calculate the magnetic field of a given current distribution. That's the new one. This is the law that allows us to calculate the magnetic field of a given current, electric current distribution. Electric current distribution. So given an electric current, a specific electric current distribution, right? What is going to be the magnetic field? And the actual equation is this one that you're going to see right in here. We're going to make some examples so you can understand how we use this specific equation, right? It's, and by the way, let me write down the electric flux, how it looks like, right? The electric flux looks like something like that. Is a function of the electric field and the area of your closed volume. Okay, and here we have something that's quite similar, but it's not. See, you have the field here. We have a field here, but here we have an area here, and whereas here we do not have an area, here we have a pass. Okay, here we have a charge that's enclosed by the area, but here we have an electric current that's enclosed not by an area, but by a pass. Once we start doing some examples, you're going to understand exactly what it means. So those two equations kind of similar, okay? But there's a major difference here. A major difference that instead of an area, here we have a length, a pass length. And instead of enclosed charge, we get an enclosed current. Okay? For the magnetic field, for the Gauss's law of the magnetic field, we get a similar equation. Notice that we have area here too, right? Area here, area here. What changes here is the electric field. And because there is no magnetic monopole existence in nature, we have a 0 on the right side of the equation. We should do our break soon, right? See, we can do our break right now. When we come back, we are going to do an example. Break 11:55 to 12:10 p.m. 11:55 a.m. to 12:10 p.m. Any questions before I go to the break? Okay, so I see you in the next 15 minutes. Wow. Okay, we're back here. Okay, so just to remind you, okay, Ampere's law is used to how to determine the magnetic field, the B field of a given current distribution. That's what Ampere's law used for. And there are some specific steps that we have to follow to find out the magnetic field of a given current distribution. Okay, then we're going to start with an example here. One possible example. One of the problems that we calculate is the magnetic field of an infinitely longer wire, straight wire, using Ampere's law. So just think about the power lines that we have out there, right? Think about those power lines that goes for kilometers and kilometers. Those power lines can be thought at each line of the power line can be thought as a infinitely long straight wire, current carrying wire. And let me get here. Let me get an illustration of one of them here. Okay, that's the torque in the loop, right? In the closed loop. Okay, the first thing that you have to know is that if you have, okay, here you go. Here's the infinitely long current carrying wire. This wire is oriented along the x-axis. And we want, for instance, to calculate the magnetic field at that spot, okay? The first thing that you have to know about the magnetic field is that you can also use the right-hand rule to determine the magnetic field around a current, okay? So look what we have right here. The magnetic field will always circulate around a current carrying wire. Will always circulate. That's an important difference between the magnetic field and the electric field. So let's take a look, and that's all implicit right in here in this law. Okay, I'm going to write that down here. No, recall, right? Recall that the electric field always starts or ends at an electric charge. The electric field starts at a positive charge and ends in a negative charge. Okay? So the electric field lines are either pointing towards or away from a charge. In other words, the electric field lines are either pointing away, like the case of a positive charge, or towards, in the case of negative charge, towards an electric charge. In the case, so you gotta memorize that, okay? In the case of the magnetic field, in the case of the magnetic field, the situation is distinct. Instead of pointing towards or away from the electric current, right? Away from, towards or away from the electric current, comma, it actually circulates around it. Can you remember that? Around it, okay? The electric field points towards or away from its source. Magnetic field circulates around the magnetic source, which is the electric current, okay? So let's write it this way: electric field either diverges, right? Or converges from its source, and the source is an electric charge. Magnetic field circulates. That's an important difference. Circulates around its source, which is an electric current. Okay, circulates. Diverge or converge. Diverge from or converge to its corresponding source, electric charge. Magnetic field circulates around its source, its corresponding source, right? Which is the electric current. And the way we illustrate it is something like the following. Here you go. Here is an electric current along the x-axis, right? Now, if you rotate the x-axis around the y-axis by 90 degrees, we are going to see something like that, okay? The x-axis is going to point towards you, and not just the x-axis is going to point towards you, but the current is also going to point towards you. And when I mean that the magnetic field circulates around the current, I really mean it. How is it going to look like? The magnetic field at a given distance from this current is going to make an angle of 90 degrees with respect to this vector position r. Okay? And when I mean by circulating, here you go. As we change the angular position of this magnetic field, we are going to draw a magnetic field distribution that's going to circulate around this wire. One magnetic field here, another magnetic field here, and so on, okay? I can even put more magnetic fields here. Here you go. Another magnetic field here, and then I'll have to orient it, make an angle. Let's see how you're going to do that. No, I don't want to do that. I want to rotate this vector. Let's see how I rotate this vector here. Position, Horizontal, there's a way to rotate. Rotation right in here. Yeah, I'm rotating. Let's see, one, yeah. At this point, it's gonna look like that. Why this one is outside? Yeah, here you go. This one is here. Okay, and we're gonna have another vector here. I'm gonna rotate it. Let's see here. Yeah. And it has to be tangent to this circle. Nope, I don't. I want rotating the other way. And here you go. Here's another vector position, right? And so on. Do you see the magnetic field circulating around the wire? That's how magnetic fields behave. Okay. Here you go. That's another illustration of the same thing that I was doing. X-axis and current coming out. And that's the path that I'm talking about. It's a closed path, not a closed area. It's a closed path around the current. Okay, if we are going to look at a different path, here you go, a path that's further away from the current, the magnetic field still circulates around it. And because now the magnetic field is further away from the source, its magnitude decreases as well. Do you see that? Because we are closer to the source, this magnetic field is stronger at this point than it is at this point. Okay? And we can calculate the exact functional relation of this magnetic field. And the steps are the following, okay? First, we recognize that the element of a current, okay, here you go. First, we recognize that an element of current is the source of the magnetic field because, okay, that's what we first do. And that has an important consequence. The consequence is the further you move away, the further you move away from the source, the weaker the magnetic field becomes. The weaker the magnetic field becomes. Just like the electric field, right? The further away you move from an electric charge, the weaker the electric field becomes. Okay, so magnetic field circulates around its source according the magnetic field circulates around the source according to the right-hand rule. Okay, how does the right-hand rule applies? Let's go back here for me to show you. Okay, the right-hand rule that we apply is the following. We orient our thumb in the direction of the current, the thumb of the right hand, and rotate the palm of your hand. The palm of your hand indicates the direction of the magnetic field. In this specific case here, the magnetic field is going to be counterclockwise. Okay? Right-hand rule. The field always circulates around its source. Okay. And I'm going to put like the direction of the B field is given by the right-hand rule. Right. The right-hand rule, okay? And how does it work? Gosh, this thing here is not working the way I want. Let's see here if I can. Okay, I got it. Let's try it again. I hate that. Let's see. Let me try. It's not working the way I want this thing. Let me try this way. Yeah, okay. Maybe it works now the way I want. Yeah, I'll have to undo it. We go 3. It was working so fine. Why it doesn't want to work? Oops. Yeah. And rule. Now, how does the okay? So point the thumb along the direction of the current, direction of flow of the current. B, circulate point the thumb with the extend along the extend, let's see, extend the palm of your right hand. Here goes. Better this way. Point the thumb of the right hand along the direction of the flow of the current. Circulate the palm of your right hand around the thumb. Okay? The direction of circulation of the palm, the direction of circulation of the palm is the direction of the B field. Okay, that's how it goes. Just like in the case of okay. Oh, and by the way, also the direction of circulation of the palm of your hand traces a closed path that is used in Ampere's law. In Ampere's law. Going back to the drawing right here. Do you see this closed path here? Here's what we call the Amperian loop. The closed path we call the Amperian loop. Okay, this closed path is also referred as the Amperian loop. Just like the Gaussian surface, right? Amperian, okay, Amperian loop. Just like we had the Gaussian surface. Very important, just like in the case of the Gauss's law for electricity, recognize that Ampere's law applies only to problems that have symmetry, just like Gauss's law for electricity, right? Not every problem can be solved using Gauss's law. Not every problem can be solved using Ampere's law. It has to have a symmetry. It has to have some geometrical symmetry for you to solve the problem. In the case, for instance, of the infinitely long wire, it does have a cylindrical symmetry with the imaginary cylinder centered at the position of the wire. Again, going back here, see what you see right in here? This closed path is generating a cylinder that circulates around, that's centered at the wire, at the position of the wire. Now let's apply Ampere's law. Right? You have almost everything that you need. Now let's apply Ampere's law. I'm going to emphasize, you already know that the magnetic field circulates around the wire. Okay? And you have this Amperian loop that is enclosing your current. Let me use this. Here we go. The Amperian loop here is enclosing this current. Okay? So in this case here, the I enclosed can be replaced by the letter I. Okay? That is only one pass. Okay, and this path is a circular one. The magnitude of magnetic field here is the same as magnitude here, and so on. So what we have to do, we have to write down, because there is only one path, right? Let's see here. We can put the number 1 here for n. We do not have like a square with 4 different passes, right? For this circular path, we have just a single path. So what we end up having is going to be just one magnetic field multiplied by a path delta L. Like that. Yeah. Okay, and what's the length of this delta L? The length of this delta L is the length of this circle, which is 2 pi r. Two, and don't forget the magnetic field is parallel to the path, right? And the path is taking, tangent to the circle. Not only the B field is tangent to the circle, but the path, the vector of this path is also tangent to the circle. So here we got 2 pi r. I'm gonna put just a B. Gosh, I didn't want that. I want this one here. Here you go. 2 pi r. And now that's the one that we do not know the value, okay? We solve it for B, just like it's a very similar procedure compared to that of the Gauss's law. 2 pi r. I'm going to boldface. It's going to be a black color. Oh, here you go. Ow. Here you go. That's the relationship that we get for the magnetic field around the infinitely long wire. That's one example. Let's look at another example. Note, see, like I told you before, right? The magnetic field will always be directly proportional to the current and will always be inversely proportional to the distance from the wire. The R is inversely proportional to R, right? Another one. Let's see here. Another problem that we can look into is that of a solenoid. Magnetic field of a solenoid, the magnetic field of a solenoid of radius r, right? What's a solenoid? What is a solenoid, right? You gotta know what a solenoid is. Solenoid is a cylindrical tube around which we wrap a single wire. Can you picture that? Let me show you here an illustration of a solenoid. Go. Okay, here you go. Here's a solenoid. It's a tube, and I wrap around this wire, and that's connected to a battery, right? And the battery powers a current along this solenoid. The solenoid is a very important device. We are going to find out this type of device in our own cars. And why is it important? It is important because it produces a uniform magnetic field here inside, okay? So by the same token that a parallel plate capacitor produces a uniform electric field within its volume, a solenoid with a uniform current distribution produces a uniform magnetic field inside it. It's possible to derive it, but it's a long process. I'm not going to do that here. It's possible to derive from magnetic field inside it and a zero field outside it. It's possible to derive the magnetic field using Ampere's law, but it is a very long procedure, okay? So all I'm going to do is to show to you what's the relationship that we have for the magnetic field. Don't forget the magnetic field of a solenoid is uniform inside it. And the relationship is like that, you know? The magnetic field for a solenoid of radius r is mu naught n is the number of wounds around the solenoid, the turns around the solenoid, divided by the length of the solenoid. Inside the solenoid is uniform field, outside the solenoid is zero. Okay, so n is the number of turns around the solenoid. L is the length of the solenoid. Can you remember that? This device, the solenoid, is so important in physics that we come up with a symbol. There's a symbol for the solenoid, for and it is we're going to see later on. The symbol for an inductor. Okay, the solenoid is the symbol for an inductor. Do you remember that I told you about one of the important component elements of electricity and magnetism, right? The capacitor. Representative of the capacitor is two parallel plates, right? But the capacitor can have all different types of geometries. But because the parallel plate capacitor has a uniform electric field in there, we adopt the symbol of the parallel plate as the symbol of every capacitor, no matter what's the geometry of capacitor that you're using. And the inductor, the symbol for an inductor is the symbol of the solenoid, right? Because it produces a uniform magnetic field. Here you go. Here is the wires, right, coming around the solenoid. This wire here, this current is pointing towards you. On the other side of the solenoid, the current is pointing into the screen. That's the step-by-step procedure to calculate the magnetic field produced by the solenoids. You already know that the magnetic field circulates around each wire. We have 7 more minutes to go. I'm just going to go through very quickly so you can understand how we calculate the magnetic field of the solenoid, okay? So taking just the single wire that you see right here, we visualize the magnetic field circulating around one of those wires. We put a second wire next to it. We visualize the same another magnetic field circulating around it. Note that this magnetic field of this wire is canceling out the magnetic field of this wire. So when you put all of that together, okay, you're going to see that there will be no magnetic field in between those two wires. Okay, that's the procedure, that's the qualitative procedure that you adopt. So what we discover is that the magnetic field is circulating around the wires of the solenoid. And then we do the same thing for the wires at the bottom of the solenoid, right? Circulating around the solenoid in the clockwise direction. We get the same canceling out of the magnetic field in the vertical direction. Okay. Here you go. Magnetic field circulating around this wire. And on the top of the solenoid, the magnetic field is circulating around this direction. On the bottom, the magnetic field is circulating around this direction. Okay, So note that, very important to note. In the next slide, you're going to see that the magnetic field of the lower wires extended all the way towards the other, okay? Strictly speaking, this magnetic field should decrease in intensity, strictly speaking. This, light green color magnetic field should decrease as it moves away from its source. But because the diameter of the solenoid is much smaller compared to its length, it's very reasonable to assume that this magnetic field is uniform from here until the other point. Furthermore, this lighter green magnetic field is going to cancel out with the darker green magnetic field. And we can apply the same reasoning for the magnetic field of the upper wires, right? And so what you end up having is going to be a magnetic field pointing in this direction inside the solenoid with approximately zero magnetic field on the outside. And this one also is going to cancel out by virtue of those other wires that are right in here, right? So that's how we derive the magnetic field of a solenoid. It's going to be on the right side of the equation. It's going to be mu naught times I. Okay. And outside the solenoid is going to be approximately zero. And then we can use this Amperian loop right here. Now it's going to be a loop with 4 branches to calculate the exact value of the magnetic field. Like I said, I'm not going to do that, but at least you have an idea how we calculate this magnetic field. Okay, we can do the same for a toroid. Okay, for a toroid let's see if I have here for the toroid in my notes. You don't have to worry about the toroids. Okay, but worry about the solenoids. And that's what we have for this chapter 21. We're done with chapter 21. We have 2 more minutes to go, right? Let me display the chapters that you have to worry about the exam. This is the section for chapter 21. Exam 2 material. 1 more minute before we go for our office hours. Here you go. Electric circuits. Syllabus, right? Chapter 20 and 21. And include also the material for labs 1 and 2. That's going to be the material for exam number 2 material. Chapters 20 and 21 plus labs 1 and 2. And then it's already 12:50. we can stop here. And I'm gonna have my office hours right now if you want to hang around, okay? So if you don't hang around, I'll see you on Wednesday when we are going to have our lab number 3. So thank you for being here and see you on Wednesday.
Thank you, Professor. Have a good day.
You too. Let's stop here.